Alright, let's take a look at the area between curves. In this particular case, we'll find the area enclosed between the curves f of x equals square root of x and g of x equals x cubed. So the first thing we want to do in order to find the area between these two curves is go ahead and plot these out. So let's go ahead and bring Desmos in to do that. And first we're going to go ahead and define f of x is equal to square root of x. And we'll define g of x is equal to x cubed. We're trying to find the area enclosed between these two curves. And if we look to the right of where they intersect here at 1, 1, you can see there's kind of area between them, but it's not really going to be enclosed on the right. There's nothing over here on the right, no curve that's going to enclose that area. But you can see here left of 1, 1 and right of 0, 0, there is an area in here that's enclosed by these two curves. So this right here is going to be our area enclosed between the curves. And what we want to note from this is that it's going from x equals 0 to x equals 1. That's sort of our interval that we're concerned with to find that area. So let's go ahead and define that and just say a equals 0 and b equals 1. So having found a and b and having noted that f of x, the red curve here, is greater than g of x, or blue curve over this interval, we really have all we need to find the enclosed area. But before we evaluate that, let's go ahead and take a closer look at this graphically. So if we look at our f of x function, it's plotted here in red. And you can see we're interested in that region between a and b here, where we define a equals 0 and b equals 1. And we want to find that area under the curve between those 2 points, which is going to look like this area shaded in red here. And of course we can find that exact area as the definite integral between 0 and 1 of our f of x function square root of x dx. And if we did the same for our blue function g of x, we found that area under the curve between 0 and 1, it would look like that region shaded in blue here. And of course we could find that exact area based on the integral of x cubed between 0 and 1. But what we're really looking for here is not the area in the red or the blue necessarily, but we're looking for the area shown here in green, which is the area under our red curve but above our blue curve. That's our area enclosed between the two curves that we're trying to find. And you can see graphically that that area in green here is just going to be our area in red over here minus our area in blue over here. So analytically, all we have to do is evaluate that integral in red and subtract this integral in blue over here. And we could do that directly, evaluating them separately. However, it's probably a little bit simpler to make this into one integral. And we can do that based on property 4 of our properties of integral that we discussed in the video linked here. And applying that property, we find that this is just going to be equal to a single integral from 0 to 1 of our f of x function minus our g of x function. So let's go ahead and remove some of these items here so we can evaluate that integral and find our answer. So first thing we're going to want to do to evaluate this integral is find our antiderivative of square root of x, which is just going to be 2/3 x to the 3/2. And then we're going to want to subtract our antiderivative of x cubed, which again using the inverse power rule is just going to give us minus 1/4 x to the 4th. And of course we want to evaluate this whole formula at 1 and 0 and subtract these two. So first thing we're going to do is go ahead and take this 1 and plug that in for our x values. And doing that, it yields this formula down here. And of course 1 to any power is just going to go to 1, so this is going to simplify pretty quick. Next, we're going to want to take this 0 here and go ahead and plug that in for x as well. And doing that, that's going to yield this formula here, and of course all these 0 terms are just going to go to 0. So this formula is going to simplify pretty quick to just 2/3 minus 1/4. And now to subtract these, we're going to want to get a common denominator. In this case, that's going to be 12. So this is going to be 8/12 minus 3/12. Subtracting 3 from 8, we end up with 5/12. Final answer. But before we go ahead with that, let's just go take a look graphically and see if that makes sense. And I think it does, because if you look at this square over here, that the area of this square is just going to be the length times the height, which is going to be 1 times 1. So this area is just going to be 1 here. And you can see the area in our green looks like it's maybe about half of the value of that square. So our answer we came up with of 5/12 definitely looks like a reasonable value for what's in the green here. So I think based on that reality check, we can go ahead and claim victory and say that we have found an answer to the area enclosed between these two curves. So to summarize, if you're looking to find the area between curves, more formally, we can say that the area A between f of x and g of x over the interval a to b, given that f of x is greater than g of x over that interval, is simply the integral from a to b of quantity f of x minus g of x dx. And that is our formula for the area between two curves.